Okay, so let's have a look at what that mechanism would look like. We have our carboxylic acid, okay, and then we have some acid in the system. So again, the first thing we're going to do is create a more reactive carbonyl group to start with. Okay, so we have protonated that oxygen, and then we're going to use our methanol, the lone pair of electrons on the oxygen, to act as our nucleophile. We then break the carbon-oxygen double bond. And we've got our addition of our nucleophile, which is positively charged. We then see some kind of proton transfer. At that point, we create this protonated water ready to leave. We have the O-methyl group. We then reform the carbonyl carbon bond, and we lose water as our leaving group. So then we end up with our new carbonyl and the O-methyl, and then the final step is just to deprotonate to give our new ester product. Okay, so that is how we would try to create an ester from attack of an oxygen carbonyl onto a carboxylic acid. In reality, this isn't necessarily the easiest way to do it, and that we would possibly use a more reactive carbonyl species to start with. So by that, what I mean is we can use things such as acyl halides or anhydrides. So if we take the acyl halide example, what we're looking at here is what we would call an acid chloride. Okay, this is very, very reactive to start with, and we'll look at why that is at the end of the lecture. So, but what we can do is we can treat this as, it doesn't need activating at all. It's so reactive to start with that the methanol can attack that as a nucleophile, break the carbon-oxygen double bond. We end up with an O- up here. We have our Cl, we have our OMeH, which is positively charged. But this is so ready to react further because the chlorine is such a good leaving group that we can reform that carbonyl carbon and immediately have chlorine leave as a leaving group. What that gives us is our methanol, which is still protonated, and then of course we know that we've got Cl- in the system. That Cl- can help deprotonate that oxygen to give us our ester product. Okay, we can do exactly the same thing with what's called an anhydride. So an anhydride has a structure where it's got two carbonyl groups linked through an oxygen. Okay, and again, this is a really reactive species, not quite as reactive as the methanol, but still pretty good. So we can take the lone pair of electrons from the oxygen again, from the alcohol. We can break the carbon-oxygen double bond. What that gives us is one of, and it doesn't matter which one, but one of the carbonyl groups reacts. We have our OMe, and then we can reform the carbonyl carbon and kick out this group as the leaving group. We'll have a look at that leaving group in a minute. So what we end up with here is OMeH, and what we end up with is this anion as a leaving group, and this is a very stable leaving group because we can draw a resonance structure where we move the negative charge across the two oxygens, and that makes it particularly stable. And then finally, we lose that proton, and we end up with our ester product. So this would be, a very simple way, or a much easier way of making our ester than doing the carboxylic acid with the acid and the alcohol. Now, if we've made an ester, that is very similar to a carboxylic acid, and so that can also be attacked by another molecule of alcohol. So if you take an ester and you take an excess of some alcohol with an acid catalyst, the result will be that you will replace the OR group in the ester with the OR group in the alcohol. So if we take an example of that, okay, so we have our ester to start with. Let's use a methyl ester. Okay, we have our acid catalyst. So the first step is the same one that we've used many a time, where we protonate our carbonyl oxygen to make it a more reactive carbonyl species. And then if we add excess ethanol, it's a different alcohol, this can now react with our charged activated carbonyl group. We break the carbon-oxygen double bond. We end up with our tetrahedral species. And then at this point, we can do, once again, our proton transfer. Okay. And again, we can add that to many different, all the different oxygens, okay? But what we're wanting to do is say, well, when we get it in the equilibrium to add here, we've then set up this methanol group as a leaving group. So we can take our lone pair of electrons from our oxygen here, reform our carbonyl carbon bond, and then kick out methanol as our leaving group. That takes us to give, we now have the O-ethyl plus methanol. Now, of course, you can see at this point, all of this is in equilibrium. So what's to stop? Just like at the start here, we had the ethanol attacking. Why we could have the methanol attack the O-ethyl ester to send us right back to the start. But of course, what I said is that we're using an excess. So this ethanol is in an excess. Therefore, it's going to outcompete the methanol. So it's going to drive the reaction away from the methyl ester to finally form, once we have deprotonated here, to finally form our O-ethyl ester instead. And this is quite an important idea, this idea of transesterification, because there are some well-known drugs that use this within their mechanism of action. So if you look at transesterification in aspirin, this is part of its mode of action. So here we've got our acetyl salicylic acid, so we've got, this is our ester, so if you look this bit here, okay, that's our ester, our OR group from the original ester, and then of course here we've got our alcohol, and this alcohol is a serine residue that's in the enzyme, the COX enzyme, and what happens normally is this serine residue is involved in producing prostaglandins, which will go on to be part of the pain, causing pain. But what happens when you get your aspirin into the enzyme's active site is a transesterification reaction. So just using the same mechanism we've just seen, where we now have our new alcohol here, and this O-serine, which is attached to the enzyme, becomes our new ester. So we've now acetylated the amino acid in the enzyme's active site, and this can now no longer do the reaction that it needs to produce the prostaglandins, and that will then lead to a pain relief response for the patient. So these kind of reactions are quite important because they do form the mechanism of action of lots of drugs. The other thing you can find is that lots of drugs with ester groups will be metabolized, so we'll be changing those functional groups within enzymes' active sites to create metabolites of the drugs or the molecules that are in our body. Another really important kind of reaction that happens with carbonyls is the idea of hydrolysis. So we've looked at using oxygen from an alcohol, but we can also use oxygen from water as our nucleophile. And so if you have a carboxylic acid derivative, so again, something like an ester, or we'll look at amides as well, if you have lots of water around, you can hydrolyze that carboxylic acid derivative to become a carboxylic acid. And that can happen under acidic conditions and basic conditions. So if we look at the acid catalyzed example, so we've got our ester here. Let's use a methyl ester again. Again, under acidic conditions, first thing we're going to do is activate our carbonyl group. So we're going to protonate that oxygen to give us a more reactive carbonyl species. At this point, we will take our slightly weaker uncharged nucleophile, and we're going to do the nucleophilic attack of the carbonyl carbon and break the carbon-oxygen double bond. That will give us our tetrahedral intermediate species. We have our O-methyl, and then we have our water that's added. At this point, we then do our proton transfer. Okay, and again, that proton transfer, it's all in equilibrium. It's moving between all the different oxygens, but at some point in the reaction, it is going to end up on this O-methyl group. And when that happens, we can reform our carbonyl carbon and we can kick out the methanol as a leaving group. So what we end up with then is a carboxylic acid. We end up with a carboxylic acid once we've deprotonated. And it's worth noting, at this point we end up with our acid catalyst back. So what about under basic conditions? So that's the acid catalyzed example. What about if we do it under basic conditions? Well, I've said base catalyzed with a question mark. So is it truly a catalytic reaction? Well, let's have a look. We take our O-methyl again, ester. Now, if we're under basic conditions, what we will have is some kind of charged nucleophile. We'll have an OH group if we put in sodium hydroxide, for example. We can use that as our very strong nucleophile, break the carbon-oxygen double bond to give us our tetrahedral intermediate again. But of course, in the past examples that we've just done, we've then done a proton transfer step. But if we're under basic conditions, we don't have a proton that we can do a proton transfer with. So at this point, we just have to reform our carbonyl carbon, and we have to have the O-methyl group as our leaving group. So we reform, and there we have our carboxylic acid, and we have our O-methyl group. Now, the O-methyl group, though, is a very strong base. It's got this oxygen with a pair of negative charge, and of course, the carboxylic acid, the acid giving the name away, it has an acidic proton. So what can then happen is that this will remove that proton to give us a carboxylate anion, which we know is quite stable because it looks very similar to the one we saw in the anhydride example, plus our methanol. And you'll notice here that this is effectively irreversible because the methanol is not going to attack this carboxylate anion, because we'll discover later on that because of this negative charge, we can delocalize that across these two oxygens, and that actually makes this carbon less reactive. So we've got an unreactive carbonyl carbon, and we've got a very poor nucleophile. So this now is essentially irreversible. So that's if we do it with an ester. Hydrolysis of an amide is another really important reaction that occurs. This is an example of something which happens in penicillin, for example. It has a very strained amide bond within its structure, and when you go to your pharmacy, the pharmacist has to take the dried penicillin or antibiotic powder and reconstitute it, dissolve it, suspend it in water just before giving it to the patient. And the reason is the moment it gets suspended in water, it's starting to undergo hydrolysis. And as it undergoes hydrolysis, as you break that amide bond down, you actually deactivate the antibiotic from working. So understanding the hydrolysis of an amide is really important. We're going to look at the reaction mechanism in a minute, but it's just worth noting at this point that amides can be hydrolyzed, but the reaction is actually a little bit slower. And there's a couple of reasons for that. The first one, and we'll cover this in far more detail towards the end of the lecture, is that the lone pair of electrons on the nitrogen are able to delocalize across to the oxygen. So we've got two resonance structures here. What this means is that the carbonyl carbon actually gets more of a share of an electrons in an amide than you might think. Okay, the same thing can happen with the oxygen, with the ester, but oxygen being more electronegative doesn't really want to do that. It doesn't really want to give up its electrons as much. So in this case, although the carbonyl carbon gets a bit of a share of this pair of electrons moving, delocalizing across the ring, or across the double bond, it doesn't do it as much as with the nitrogen. So the nitrogen just gives that little bit more stability to that delta positive charge on the carbon, which makes it less reactive. And we'll cover that towards the end of the lecture, just the idea of how delta positive that carbon is, how that arranges or how that deals with its reactivity. The other thing just worth noting is that if you have acid present, then you do run the risk of protonating the nitrogen. And so if you protonate the nitrogen first, you can't do that resonance stabilization. But the other thing is, if you protonate on the oxygen when you first start this reaction mechanism, then you still have this ability of these nitrogen lone pair to delocalize across the bond. So by adding the acid in the first step, we will actually predominantly form this kind of protonated oxygen rather than protonating the nitrogen. So let's look at the acid catalyzed example. So we have our amide. Okay, and the first thing we're going to do, as I've just said, is protonate the oxygen, because we know that the amide isn't quite as reactive as we want it to be. So we're going to end up with our, and we also know that it's going to predominantly protonate on the oxygen rather than the nitrogen, because that still allows this resonance structure to form. And then we're going to take our kind of weaker nucleophile and attack our activated carbonyl. We're going to break the carbon-oxygen double bond. That gives us our tetrahedral intermediate. We are back under acidic conditions, so we can do our electron transfer. So that at some point we say, well, we have NH2 and we protonate here. We can then reform our carbonyl carbon and kick out the amine. Of course, we still have our proton up here to give us our positive charge, and then we also have our amine here. And then the final thing is we can deprotonate, and actually the amine can help us do that. We don't need to worry about that too much at the moment though, to give us our product at the end. What is just worth noting that actually, yeah, the amine would pick up that proton and become positively charged, so then that becomes a very weak nucleophile, so that wouldn't be involved in the reaction, and further on we would still get the water attacking for the hydrolysis. That's the acid catalyzed reaction. What about in basic conditions? Again, we have a question mark, which should give you a hint that perhaps it's very, very similar to the ester, that it won't be base catalyzed. So we can have our, this time we're just going to do NH2 just to show you it doesn't matter. So we've got our very reactive nucleophile. That's going to react with our unactivated carbonyl, break the carbon-oxygen double bond. We get our O-, we get our NH2, and we get our OH. We have our tetrahedral species again. We don't have any protons, so we can't do proton transfer. If we lose the OH, the leaving group, we just go back to where we start. If we lose the NH2, then we reform our carbonyl carbon, and we reform our carboxylic acid. We have this NH2- as our leaving group in solution. That's going to act as a very strong base, and so it's going to react with this hydrogen here to again give us this kind of effectively irreversible carboxyl anion and NH3 as the other partner. Okay, so under basic conditions, we aren't regenerating our base, so therefore it isn't base catalyzed. It happens, but for every molecule of carbonyl group you have, you need one molecule of your base. It's worth just noting here that sulfur acts in exactly the same way. So if you have a sulfur nucleophile, so a thiol, it will do exactly the same thing as the alcohols we've just seen. Again, it's just worth noting that thiols are actually more reactive than oxygen nucleophiles, and that's because their size make them a better nucleophile. The electrons are in an orbital that's further away from the nucleus, and so actually they're more available for reacting. And that's the same reason why our S- is actually a better leaving group, because that sulfur, those electrons are in a much bigger orbital, and so they're more happy to be negatively charged. They can be stabilized through this large orbital. So just an example, if you had your anhydride, you react it with some kind of thiol, or you would end up with a thioacid, and the same with if you took an acyl chloride with some kind of thiol, you'd end up with a thioester. Okay, so here's just a chance for you to have a practice at that. So here's one example. So you need to take an acid chloride, so a quite reactive species, react it with an alcohol in the presence of a bit of base, and then you get a product, and then that product you then take and you treat with acid and water to give you a carboxylic acid.